Okay, in this video we're going to talk about kinematics in two dimensions, but it's a special type of kinematics in two dimensions. This is what we call projectile motion. I'd like to start out with this question. We have a cannonball being fired horizontally at an initial velocity of 308 meters per second from the top of a cliff. The height of the cliff is given as 19.6 meters. How far from the cliff will the cannonball be before it splashes into the water? And what will be the final speed of the cannonball just before splashing? I'd like you to give some thought to what question 1 is asking in terms of the variables that we have in our various kinematics equations. What is that variable for question 1? It's how far, so it's a displacement, like a delta x or a delta y, but which direction are they talking about? They're talking about how far it will be horizontally. They're talking about delta x. They gave us a velocity in the x direction, but they gave us a height in the y direction. So how do those work together in an equation? Are we allowed to just plug those together into the same equation? One of them is in the x direction, one of them is in the y direction. So we have this video to demonstrate exactly that. I don't know who Alan is, but he's some very nice physicist who has decided to set up some lab equipment to demonstrate something really important to us about motion in two dimensions. As it says down the left side of the screen here, what's happening in one direction or one dimension does not affect what's happening in another dimension. So he's taking out this equipment, he's making sure it's nice and level. He's going to use this spring-loaded device to drop an object. It's going to drop this ball straight down with no initial velocity. But it's also, on the other end, going to launch this different ball horizontally. So simultaneously, one's being dropped, one's being launched horizontally from the exact same height. The two balls hit the ground at the same time because they fell the exact same distance, and it's the exact same acceleration due to gravity pulling them down. Neither one of them had an initial velocity in the y direction. So gravity pulled them down from an initial velocity in the y direction of 0, and it's negative 9.8 meters per second for each. As it says on the left side of the screen here, the sideways motion of the object is not changed if the object is also falling. Or to put it another way, the falling of the object does not change anything about its sideways motion. And that's the whole key to projectiles. Let's take a look in a little more detail. Let's take this question, which might look really familiar in terms of how to do it, because I haven't asked this exact question, but it is very much like the kinematics problems we've already been doing. A cannonball is accidentally dropped from the top of a 19.6 meter tall cliff. Dropped means you know the acceleration, negative 9.8 meters per second. And the word dropped also tells us that the initial velocity of this cannonball is 0. Its displacement is 19.6 meters downward, so we would say it's a negative 19.6 meter displacement. The question is, how fast will it be going when it reaches the water? We could solve for this probably using the time-independent equation of kinematics, the v final squared equals v initial squared plus 2a delta y. Determine the time it takes to reach the bottom of the cliff. We have several equations that we could use to reach the to determine the time, because we know so many other things about it. So I went in and used the time-independent equation and found v final is negative 19.6 meters per second in the y direction. And I determined the amount of time it takes the cannonball to fall the 19.6 meters downward is 2.0 seconds. The term projectile means that the object that we're studying is only experiencing the force of gravity. So it is only experiencing a delta v in the direction that gravity is pulling it. It is being accelerated downward at 9.8 meters per second. there is no force pushing a projectile in the x direction. So horizontally, it has no change in its velocity. Its velocity is whatever it was to start. So in the previous problem where the cannonball was dropped, it had no sideways motion and nothing would cause it to gain sideways motion. Most people don't so much have a problem with that when we're studying projectiles. The part that's initially a little bit tough to believe is if a cannonball is fired with some horizontal velocity, as it's falling, it will just continue moving at that horizontal velocity while it also happens to fall. That's what this image here is showing us. If you look at the gravity-free path on your screen, it's trying to show you where the cannonball would be. Let's say it's fired at 308 meters per second, like in our opener to this video. Then every second it would move out horizontally 308 meters. If there was no gravity, it would just do that in a straight line. Because there is gravity, what it instead does is it moves out 308 meters every second while also falling at an acceleration of 9.8 meters per second. As it says at the bottom of left of the slide, it follows all of the equations and laws of kinematics that you've already studied. In the x direction, it's moving at a constant velocity. Acceleration is 0. In the y direction, it's moving at a constant acceleration, negative 9.8 meters per second. So let's go back to that question from the very beginning. The cannonball is fired at 308 meters per second from the top of a cliff. The cliff is 19.6 meters tall. How far from the cliff will the cannonball be when it splashes into the water? I decided I like this delta x equals v initial x delta t plus 1/2 a delta t squared equation. And the reason I like it in the x direction is because the acceleration in the x direction is 0. So this is going to turn into delta x equals velocity initial in the x direction times time. This is actually something that you would have learned about like in middle school. We talk about distance equals rate times time. So this has turned into a really simple problem that the cannonball is going to go 308 meters every second moving away from the cliff. The problem is I don't know how many seconds it's going to do that for before it hits the water. So first I need to solve for delta t. I can't solve for delta t in the x direction because I don't know enough information in the x direction. What I need to do for a projectile problem, almost always what I need to do, is solve for time in either the x or y direction and then use that time that I solved for in the other dimension. No other variable besides time can be moved from the x to the y. If you're trying to calculate something in the horizontal direction, like 308 meters per second in the x direction here, and you put in any numbers that are vertical, like negative 9.8 meters per second, or the 19.6 meter tall cliff, that's a y direction piece of information, and the 308 is an x direction piece of information. Putting them in the same equation is a lot like taking question 2 and question 6 from a homework assignment and just picking some numbers from each and putting them together. It doesn't work. You can't do that. And like I said, time's the exception. So what we'll do is solve for how much time does it take the cannonball to fall 19.6 meters. We solved that a little bit ago with the cannonball that was just dropped 19.6 meters. It took 2.0 seconds. So this one that's moving 308 meters per second sideways will also take 2 seconds to hit the water. It's just that it'll hit the water much farther away from the cliff than the one that fell straight down. I solve for it this way. Delta y is equal to v initial in the y direction, which is 0 because this cannonball is fired horizontally. Delta t plus 1/2 acceleration in the y direction, which we know, times delta t squared. So I went in and solved this for delta t is 2 seconds. I can then say in the x direction, the initial velocity of 308 meters per second times 2 seconds plus the 1/2 acceleration times delta t squared, where the acceleration in the x direction was 0, so that whole part of it disappears. Meaning that how far away this cannonball is from the cliff is just 2 seconds times 308 meters per second. It will be 616 meters away from the cliff when it hits the water. And if just as you fired this cannonball, I dropped another one from the exact same height, the two would hit the water at the exact same time, just 616 meters apart from each other. That's all. There was a second question on the opening slide from this video, and that was, what will be the final speed of the cannonball just before splashing into the water? The interesting thing about this is that in the x direction, you already know the speed was 308 meters per second, and that hasn't changed. There's nothing that would cause this to have a delta x. A delta v, 308 meters per second. But in the y direction, it has picked up some velocity. It started out at 0 velocity in the y direction. It accelerated downward, and by the time it gets to the water, just as it's about to hit, it's moving 19.6 meters per second downward. The combination of the two can be found using the Pythagorean theorem, because this cannonball will be moving down and away from the cliff simultaneously the whole time that it's in motion. When it gets out to the place wherever it hits the water, it has a velocity in the x direction of 308 meters per second, in the y direction of 19.6 meters per second, for a total of 308.6 meters per second. This is an image from the textbook. It is just here to emphasize exactly what we've been talking about. It's the exact same concept. These arrows are here to represent that the blue ball and the red ball, as they fall, you'll see that their velocity vectors get bigger and bigger and bigger in the y direction because gravity is pulling it down. Notice that neither one of them has a change in their horizontal velocity vector. Red has no horizontal velocity vector the whole time. The blue one has this constant horizontal velocity vector the whole time. I can't overemphasize, that is the whole point of projectiles. That's the whole thing that you need to know to make projectiles work. So let's practice some and verify that it really is as easy as I'm making it sound.